Welcome to Teolumen Insights, where we reveal the hidden forces that shape the way you live and show you how to use them to create real transformation and supercharge your health, mindset, and daily life. Here are your hosts, Emma Greenwood and Nathan Sinclair.
Welcome to Teolumen Insights, everyone. I'm Nathan Sinclair.
And I'm Emma Greenwood.
And today we're taking a deep dive into some pretty mind-blowing areas of physics and engineering. You know, like those science fiction ideas, reaching for the stars, communicating across incredible distances instantly.
Exactly. We've got a fascinating collection of sources here, all looking at these big questions. We're talking subspace communication, things like warp drives for propulsion, and even, the role of something like the Higgs boson.
Now, for our listeners out there, it's clear you're already interested in this cutting-edge science. So we're going to try and extract the most interesting and important parts from all this complex material, make it understandable without drowning you in technical jargon.
Right. So think of it as a shortcut to grasping some really wild concepts. To lay out our path today, we'll be hitting several key points. First up, the super mysterious idea of subspace communication. What could even make that work, the mechanisms behind it?
Then there's a connection, and it's highly speculative, I've got to emphasize that, between the Higgs boson and this idea of intergalactic subspace communication. We'll get into that.
We'll also dive into quantum tunneling. Could that actually be a way to send information? Then, zooming in a bit, at least on a galactic scale, we'll look at electrogravitic hyperdrive and something called micro-warp drives.
Or bubbles, too.
Yeah, warp bubbles for, intercontinental travel. That's a mouthful.
Definitely. And last but not least, we'll touch on those iconic warp coils and warp nacelles, how science fiction imagines them, and what actual physics says about their possibility.
Exactly. So our goal here is to investigate the theory, the challenges behind each of these ideas, and all based on what we've got from the sources. A realistic look at the possibilities, the limitations as we understand them today.
Sounds good. So let's jump right in. Subspace communication. What even is it?
Right. It's straight out of science fiction. But our sources do offer some insights into its potential as actual science. One big thing they highlight is that we don't even know what subspace is.
Yeah, we're used to communication using the electromagnetic spectrum, radio waves, light, all that. But subspace, well, it would need something completely different.
Absolutely. It's like our current physics has no concept of a medium for subspace. So its very existence, let alone communication through it, that's a massive leap.
It's like trying to build a radio to pick up signals from another universe.
And we haven't even fully explored our own radio spectrum yet. It might require a whole new understanding of reality.
Whoa. Okay, so how do the sources even begin to address that?
What's intriguing is they suggest this new mechanism might be found in the principles of quantum physics, or maybe even involve the existence of extra dimensions, like beyond the 3 spatial and 1 time dimension that we experience. It's pretty mind-blowing.
Extra dimensions, that's getting pretty out there.
Right, but imagine if we could tap into those fundamental levels of reality. We might not only find new ways to communicate instantly over huge distances, but also discover completely new types of energy, or even unlock ways to travel faster than light.
Remember those from Star Trek? We can see if there's any real physics behind those science fiction favorites.
Imagine you can compress space in front of your spacecraft and expand space behind it. You create a bubble of distorted space-time, and the spacecraft sits inside this bubble, in a region of normal space.
Wow. But I'm guessing the sources mentioned it's not exactly easy to do any of that.
Oh, definitely not. They emphasize that achieving even one of these breakthroughs is insanely complex. It's like you're tackling one huge scientific challenge, and solving it could open the door to a whole bunch of other major discoveries, each equally tough to figure out. We'd need breakthroughs in materials, energy generation, and signal processing that are, light years beyond what we have now.
Right, and even if we somehow figure out the theoretical side of how subspace communication might work, actually building a system to send and receive those signals, it seems impossible.
Yeah, they draw a comparison to the limitations we already have with things like high-speed satellite communication, which is pretty advanced stuff. Now take those challenges, make them way, way bigger, and apply them to something we barely understand. It's mind-boggling.
So we're talking about needing materials and devices with capabilities we can't even imagine right now.
Exactly, pushing the absolute limits of what's physically possible.
Okay, let's say hypothetically we overcome those huge engineering challenges.
Yeah.
Then what?
Then we face the problem of noise. Every communication channel we use now has some interference, right? Like static on a radio or distortions in fiber optics. The sources suggest that in subspace, these limitations could be exponentially worse. It's not just sending a signal, it's sending a signal clear enough that you can get information out of it. You try to have a conversation in a hurricane, it's impossible with all this potential noise.
It makes you wonder, like, what's the signal-to-noise ratio in a realm we know nothing about?
Right. It's a fundamental question. And speaking of things we don't fully understand, the sources do mention quantum entanglement as a possible factor in subspace communication.
Entanglement. That's where two particles are linked, no matter how far apart they are, right?
Exactly. And while they don't go into specifics on how entanglement could be used, it hints at a way to bypass the usual limits of sending signals through space, especially that pesky speed of light barrier. It's a connection that doesn't make sense in our classical understanding of information transfer.
So, wrapping up subspace communication, it sounds like it's still in the realm of science fiction.
For now, yes. But the sources don't rule it out as impossible. They emphasize that exploring the laws of physics really deeply and discovering and manipulating new materials could maybe make it real one day.
But it's a long shot, right?
Oh, definitely. It's a very long-term, super ambitious goal. It would need tons of effort from research teams across a bunch of different scientific fields, like an audacious long-range project.
Okay, let's move on. We're going even deeper into the theoretical now with the Higgs boson and intergalactic subspace communication.
Right, this is where things get really speculative, but potentially super impactful. To even start thinking about this, we need to understand the Higgs boson and the mechanism behind it, the Brout-Englert-Higgs mechanism. It's kind of a big deal in particle physics.
So refresh my memory, what does the Higgs boson actually do?
It explains how particles got mass after the Big Bang. Before this mechanism, all particles are thought to have been massless, moving at the speed of light. Think of it this way. The Higgs boson is why things have mass. There's this thing called the Higgs field, right? It's everywhere, invisible, like an ocean. When particles move through this field, they interact with it. The more they interact, the more resistance they feel.
And that resistance, that's what we experience as mass. Okay, so no mass, all speed. Then what?
Enter the Higgs field, which is all over space, and is what the Higgs boson interacts with. Basically, particles interact with this field, and that interaction gives them their mass.
So more interaction, more mass.
Exactly. The more strongly a particle interacts with the Higgs field, the heavier it gets. The ones that weakly interact stay pretty light.
I see. And we've actually measured this.
We have. And the measurements of how the Higgs boson interacts with other particles, like the W and Z bosons, the heavy quarks, and leptons like the tau and the muon, all line up really well with the standard model. You know, the theory we use to describe these fundamental particles and forces.
It's amazing we can even measure this stuff. But the sources say our understanding is far from complete, right?
Right.
So what's missing?
That's the thing. Even with these successes, there could be a whole lot more to discover about reality. Maybe there's physics beyond the standard model, new particles, new forces, or changes to our existing theories affecting things we haven't observed yet. That's why research at places like the LHC at CERN is so crucial. They're pushing the boundaries, trying to find clues to this new physics.
It's like we've only just scratched the surface.
Exactly. And one thing scientists are looking at closely is the Higgs boson's self-interaction, how it interacts with other Higgs bosons. Understanding that could tell us a lot about the Higgs field itself and how mass is actually generated.
Self-interaction, huh? How do they even study that?
The main way is by trying to measure the production rate of di-Higgs bosons. That's when two Higgs bosons are produced at the same time in those high-energy collisions at the LHC.
Two at once. Sounds rare.
Incredibly rare. The standard model predicts it happens much less frequently than single Higgs bosons. It's like trying to find a specific grain of sand on a beach.
So how can they even hope to find them?
It's tough, but they keep searching because any difference from what the standard model predicts, like a stronger Higgs self-coupling or other undiscovered particles that could mess with the Higgs boson, could make these di-Higgs events happen more often. And if that happens, they might be able to see them, even with the limited data we have now.
So finding more di-Higgs bosons than predicted would be a huge deal.
Huge. It would mean there's new physics at play, something beyond our current understanding. The sources mentioned the CMS collaboration. They've been working hard on this. They're analyzing tons of data from the LHC, trying to put limits on the Higgs self-coupling, which is represented by lambda or...
Okay, so lots of complex research going on. But how does this all connect back to subspace communication, especially on an intergalactic scale?
Right, so we have to be very clear here. The sources we have don't directly connect the Higgs boson to subspace, but we can speculate, think about how these ideas could maybe intersect way down the line.
Speculation is always fun. Let's hear it.
So our knowledge of fundamental forces, particles, all that is always evolving. Researching the Higgs boson and the Higgs field could lead to discoveries about the fabric of space-time itself, like its structure, its properties, and how we might be able to affect it.
You're saying that by understanding how particles get mass, we might learn how to manipulate space-time.
It's a long shot, but it's possible. Imagine if we could manipulate space-time at a fundamental level. It could lead to things that seem like science fiction right now, like faster than light travel or instantaneous communication across the galaxy, maybe even by creating some kind of artificial subspace.
So the Higgs boson research might accidentally unlock the secrets to interstellar travel.
You got it. This is all theoretical, of course, but it highlights how seemingly unrelated areas of research can sometimes come together to create wild new possibilities.
That's what makes science so exciting. Okay, let's shift gears now to a different but equally mind-blowing concept: quantum tunneling and its potential for communication.
Quantum tunneling? It almost sounds magical. Our sources explain that it's a real phenomenon, proven by experiments where particles can pass through energy barriers they shouldn't have the energy to overcome. Quantum teleportation is about transferring the quantum state of a particle, not the particle itself. Imagine you have a qubit, a quantum bit of information.
Okay, got it.
With quantum teleportation, you can send the information contained in that qubit to another location instantly without physically moving the qubit.
That's wild.
It's like sending a blueprint for the quantum state, not the state itself. It's like imagine a ball rolling into a wall and then just popping out the other side.
Definitely not how things usually work.
Not in the everyday world, no. But at the atomic level, it's a different story. The sources talk about experiments with ultra-cold atoms trapped in optical lattices. You can think of those like three-dimensional grids made by intersecting laser beams. They trap and control individual atoms very precisely.
So scientists are watching these trapped atoms, and then what?
They've seen these atoms tunnel between spots in the lattice, even though they don't have enough energy to get over the barriers between those spots. And get this, they've found ways to control this tunneling.
So it's not just random. They can actually make it happen.
Right. They've observed density-induced tunneling, which means the tunneling is affected by how many other atoms are nearby. It's like the atoms are working together in this quantum world.
Quantum teamwork. I like it.
Right. And this brings us to something called bound states in the continuum, or BICs, and bound states out of the continuum, BOCs. There's specific types of quantum states that can exist in these systems, and they influence the tunneling process.
BICs and BOCs, so what do they do?
Well, under very specific conditions, like adjusting the frequency of those lasers that create the optical lattice, you can see some strange things happen. You can get a stable but uneven distribution of atoms across the lattice, or even have atoms constantly oscillating, tunneling back and forth between certain spots, all guided by their wave nature.
Hold on, their wave nature.
Yeah. Remember, in the quantum world, particles can act like waves. It's called wave-particle duality, so these matter waves can mediate the tunneling. And the sources point out that this is totally different from what classical physics would predict. Normally, the system would just settle into the lowest energy state and stay there.
So quantum mechanics is doing its own thing, breaking the rules of classical physics.
Exactly. And the really interesting part is that they can control this tunneling over relatively long distances within these systems. It hints at the possibility of controlling quantum information over larger scales, even though using it for interstellar communication is still, way out there.
So we're talking about potentially using quantum mechanics to send messages, maybe even across interstellar distances. That's pretty wild.
Wild, but the sources don't actually propose a way to use tunneling for sending messages across the galaxy. That's a huge leap from what we can do now with atoms in a lab.
Yeah, teleporting messages across light years is still firmly in the science fiction category.
For now, yes. But these experiments demonstrate an amazing level of control over individual quantum particles and show that quantum effects can happen over surprisingly large distances. So it's not crazy to think that future research might find ways to use these principles for communication over much larger distances.
It's another example of how exploring the quantum world can lead to unexpected and potentially revolutionary technology. Okay, let's move on now to something a little more concrete, at least in terms of the physics involved. Electrogravitic hyperdrive and microwarp drives.
Right. This section dives into some less established and maybe more controversial ideas. Let's start with electrogravitics. The sources talk about a period of interest in this idea, mainly back in the 1950s, particularly by some aerospace
Now,
companies.
electrogravitics, what's the basic idea there?
The idea is to create thrust, a pushing force, without needing to expel any propellant. You do it by manipulating the gravitational field directly using strong electromagnetic fields. Think of it like controlling gravity with electricity and magnetism.
Controlling gravity with electromagnetism sounds like something out of a comic book.
It does, right. And there's this theory, Heim's unverified quantum theory, that gets mentioned sometimes in discussions of electrogravitics. It suggests a way to convert electromagnetic energy into gravitational energy using hypothetical particles called gravitophotons.
Gravitophotons. Never heard of those.
It's important to know that Heim's theory hasn't been proven. It's not part of mainstream physics, and there's no experimental evidence to support it.
Okay, so gravitophotons might not be the answer. What other approaches are there within electrogravitics?
Another idea is to use powerful magnetic fields created by superconducting coils. The hope is that these fields could interact with gravity in a way that creates thrust, counteracting the force of gravity.
So, fighting gravity with magnets.
Pretty much. But the problem is that keeping those magnetic fields strong enough for propulsion would take insane amounts of energy. It's not really feasible with our current technology.
So not very practical.
Right. And when we think about using this for something like intercontinental travel, the challenges get even bigger. The energy needed for any noticeable electrogravitic effect seems to be way beyond what our current propulsion systems can manage.
So not great for getting around Earth. What about in space?
Even in space, there are issues. In Earth's atmosphere, there's something called ion wind, which is basically the movement of charged air particles caused by strong electric fields. This ion wind effect would likely drown out any weak electrogravitic force we could create.
So we need a vacuum for it to work.
That's the idea. So, based on what our sources say, using electrogravitics for propulsion, especially for something like intercontinental travel in the atmosphere, faces huge fundamental problems. Mainly, the crazy amount of energy it would need and the need for a vacuum environment.
Okay, so electrogravitics might not be the best bet. Let's talk about another idea for fast travel, maybe even faster. Micro-warp drives, or warp bubbles.
Right. The warp bubble, it's a staple of science fiction, especially Star Trek. It's such a cool concept. The sources explain that the basis for this lies in Einstein's general theory of relativity.
Relativity says nothing can travel through space-time faster than light, right?
That's right, but it doesn't rule out the possibility of space-time itself expanding or contracting faster than light.
So it's not the object moving faster than light? It's the space around it.
Exactly. That's the core idea behind a warp drive. You'd create a bubble of space-time around your spacecraft. In front of the ship, space contracts, and behind it, space expands.
So the ship is just sitting inside this bubble of normal space-time, and the bubble itself is what's moving.
Precisely. And because it's space-time that's moving, not the ship through space-time, it could theoretically allow for faster-than-light travel without breaking Einstein's speed limit.
That's pretty clever.
Yeah.
But I'm guessing there's a catch.
Oh, a big one. The sources stress that you'd need something called exotic matter with negative energy density to make this warp bubble work. This negative energy would be needed to make space contract in front and expand behind the bubble.
Negative energy, is that even a thing?
Quantum field theory does predict the existence of negative energy, but right now we can only create tiny amounts of it in very specialized labs. We're nowhere near the scales needed for a warp drive.
So not only is it hard to create, but we also need a ton of it.
Exactly. That's the second problem, scalability. Even if we could harness negative energy, we have no clue how to scale it up to the massive amounts a warp bubble would need. Some estimates say you'd need energy exceeding the entire output of our sun. We're talking planet-scale energy here.
So interstellar warp drives are pretty much out of the question.
Not necessarily. There's this idea of micro-warp scaling. You'd basically shrink the warp bubble way down, which could theoretically reduce the energy you'd need.
So instead of going to another star system, we could maybe travel quickly between continents.
That's the hope. But even at that smaller scale, you'd still need exotic matter with negative mass, or maybe find a way to use quantum vacuum fluctuations to keep the warp field stable and prevent it from collapsing immediately. And the level of control you'd need over these space-time fields would be insane. Any instability could cause some seriously bad space-time distortions.
So micro warp drives, while more feasible than the larger ones, are still super difficult.
Extremely difficult. The sources indicate that even a small warp bubble would likely need energy comparable to what stars produce. So unless we have major breakthroughs in energy storage or figuring out how to make stable negative mass, it's not happening anytime soon.
Okay, so warp drives, whether big or small, face huge energy hurdles. What other options are out there?
There's one more idea we should talk about. It's this unconventional perspective on anti-gravity, a kind of warp drive, and it's attributed to a guy named John Faust.
And John Faust, interesting. Tell me more.
This idea doesn't rely on negative energy like the other warp drive theories. Instead, it focuses on momentum transfer as a way to achieve propellantless propulsion and even warp-like effects.
Momentum transfer, like the idea that for every action, there's an equal and opposite reaction?
Exactly. He starts with a thought experiment. Imagine a container with 2 guns inside, firing bullets in opposite directions. Because the bullets travel different distances before hitting the walls of the container, there's a tiny delay in how they transfer momentum to the container. This creates a net movement in the direction of the bullet that traveled a shorter distance.
Okay, I see where he's going with this.
Yeah.
But bullets in a container aren't exactly practical for a warp drive.
Right, so the next step is to replace the guns and bullets with water nozzles. The water jets fire in opposite directions. The key point is that the jet closer to its target wall exerts more force because of the inverse square law. The force gets weaker with distance.
So the difference in force pushes the container in a specific direction.
Exactly. And this is seen as propellantless propulsion because the water, the propellant, is contained within the system and reused. Then, Faust takes this idea and makes the relativistic leap. He argues that this is creating a warp drive effect because shortening the distance for one water jet is, in a sense, contracting space and time in that direction.
So by manipulating the distance the water travels, you're manipulating space-time.
That's the argument. The longer distance for the other jet would correspond to an expansion of space and time. So he's claiming that this creates simultaneous contraction and expansion of space-time, just like a warp drive.
And what does this warp bubble look like in his model?
He describes it as a sphere with 2 small opposing cones at the front and back. Those cones are where the space-time contraction and expansion happen. The water jets fanning out as they travel represents the expansion of space-time, and the shorter path for the other jet represents the contraction.
Okay, I'm following. So where does the lower energy requirement come in?
The argument is that you only need to manipulate those 2 conical regions, not the whole bubble. The difference in negative energy densities created by the contraction and expansion is what drives the motion.
So a smaller area to manipulate means less energy needed.
Exactly. He claims this could achieve anti-gravity propulsion using existing technology, no exotic matter or massive energy inputs needed.
That's a bold claim. But I imagine there's some skepticism around this model.
Definitely. This model and its take on warp drive physics are not widely accepted by mainstream science. It would need a lot more theoretical and experimental work to prove it's viable and doesn't contradict established physics.
Makes sense. Okay, let's move on to the components often associated with warp drives. Warp coils and warp nacelles. Most people know these from Star Trek, right?
Absolutely. They're iconic. They're what let the Enterprise go to warp speed and travel faster than light.
So what do our sources say about how these things would actually work?
Interestingly enough, they don't give any detailed scientific descriptions of warp coils or warp nacelles. We have to infer their purpose and design from the broader warp drive discussions, especially the Alcubierre warp bubble concept we talked about.
So based on our understanding of warp bubbles,
Yeah.
what can we guess about these components?
We know warp drives would need negative energy density and the ability to manipulate space-time to create that faster-than-light travel. So warp coils and nacelles would probably be the parts responsible for generating and controlling those fields of negative energy.
So they'd be like the engines of the warp drive.
Exactly. They'd create and maintain that warp bubble around the ship, making space contract in front and expand behind. It's important to remember that some newer theories, like Eric Lentz's work, suggest that warp drives might not need negative energy at all. If those ideas turn out to be right, it could mean we need different designs for the parts that generate the space-time distortions. Maybe not coils at all.
Right. The tech could be totally different from what we imagine. Speaking of pushing the boundaries of what we know, what about this warp factory toolkit? What is that?
That's a fascinating development in warp drive research. It's a powerful computational tool specifically designed to model the complex spacetimes that warp drives would create. It's a set of computer programs that allows researchers to simulate and analyze different warp drive geometries. It's a big deal because before, most of the work on warp drives was done analytically.
Meaning they were trying to solve Einstein's equations by hand, right?
Exactly. But gravity is nonlinear, so finding exact solutions is really hard. You usually have to make simplifying assumptions, which means you're not looking at the whole picture.
So this warp factory, it lets them simulate more realistic warp drive scenarios.
Right. They can use numerical methods to approximate solutions, even for complex geometries that wouldn't be possible to solve analytically. It does this by simulating Einstein's field equations, the ones that describe how mass and energy warp spacetime. It also calculates the energy conditions, which are basically rules that any physically realistic solution has to follow.
So it's like a virtual testing ground for warp drive ideas.
You got it. What makes Warp Factory really useful is that it can analyze all sorts of warp drive geometries, even those too complex to solve with just math. It can figure out key properties of the spacetime, create visuals of the warp bubble, and see how energy and momentum are distributed within it.
So scientists can use this toolkit to see if their warp drive designs actually make sense, whether they break the fundamental laws of physics.
Exactly. And those energy conditions you mentioned are basically those fundamental laws. Warp Factory helps separate the plausible ideas from the ones that are just mathematical fantasies.
Okay, so how does it determine if a warp drive design is plausible or not?
One important aspect is checking if the energy conditions are met. These conditions basically say that energy density should be positive for all observers, no matter their perspective. Warp Factory calculates these values from the viewpoint of many different hypothetical observers, called Eulerian observers. If any of those calculations come out negative, it means the design violates the energy conditions and is probably not physically possible.
So it's like a reality check for these warp drive concepts. What other things can Warp Factory do?
It can also visualize how momentum flows within the warp drive spacetime. That helps understand how the energy is moving and being transported by the warp bubble. It can also analyze geometric features of the spacetime, giving us a better understanding of how the warp drive curves spacetime.
Pretty comprehensive. And they've used this toolkit to analyze the Alcubierre metric, right?
Right. Warp Factory confirmed what Alcubierre originally found. His metric needs negative energy density, which violates those energy conditions we talked about. That's because of the way it makes space contract in front and expand behind.
So back to that negative energy problem.
It's a recurring theme. But it's not just for analyzing existing metrics. Warp Factory has also been used to look at modified versions of the Alcubierre metric, where scientists have tried to tweak the math to get rid of the need for negative energy.
So tweaking the design to make it more physically possible, what kind of modifications have they explored?
One thing they've tried is changing the time component of the metric. Warp Factory lets them see how these changes affect whether or not the energy conditions are met, and often it leads to different patterns of violations compared to the original Alcubierre metric.
So still working on that negative energy problem.
Right. They've also analyzed the Lentz-inspired metric, which tries to avoid negative energy by using shift vectors that point in multiple directions. Warp Factory shows that this creates a complex, donut-shaped flow of momentum, especially in directions perpendicular to the warp drive's movement.
Interesting. So different designs, different challenges. What about this idea of a co-moving frame?
Warp Factory can do that too. It transforms the warp drive equations into a frame of reference where the warp bubble appears stationary. This simplifies the math by getting rid of the time dependence, but it introduces a shift vector into the spatial part of the equations.
So a different perspective on the same problem. Does it help get rid of the need for negative energy?
Unfortunately, no. Even in the co-moving frame, the Alcubierre metric still needs negative energy density to work.
Okay, back to square one. The sources mentioned some specific energy conditions. What are those all about?
Right, there's the null energy condition, or NEC, and the weak energy condition, or WEC. These are basically rules about the density and flow of energy in spacetime. Warp Factory checks if these rules are being broken.
And how did it do that?
It calculates these energy conditions from the perspective of tons of different observers, those Eulerian observers we talked about. If any of the results come out negative, it means the energy condition is violated and that warp drive design is likely not possible.
Got it. So a negative result means back to the drawing board.
Exactly. Now, here's a really interesting finding from Warp Factory. They developed a theoretical model called a constant velocity warp shell solution. It tries to create a warp drive that follows the energy conditions by using a shell of regular matter and a specific configuration of the shift vector.
So no exotic negative matter in this model.
That's the idea. The analysis shows that the energy density of this warp shell is similar to a normal moving shell, but that shift vector changes the momentum and pressure as seen by different observers. And the best part is, it seems to satisfy all the major energy conditions.
So it might actually be physically possible.
It's a step in the right direction. Another cool thing about Warp Factory is that it can simulate how light travels through these warp shells compared to regular matter shells.
Light traveling through warp bubbles, that's got to be interesting.
It is. They've found that light experiences a slight time delay when it passes through a warp shell compared to a normal matter shell. This delay is similar to an effect seen around rotating black holes called frame dragging. And the fact that this time delay is something you could measure means that the shift vector in this warp shell model is having a real physical effect. It's not just some mathematical trick.
That's pretty convincing evidence that this model might be on the right track.
Right. And then there's the idea of using spherical shells of matter with a specific type of mass, called ADM mass, to potentially make warp drives with positive energy.
Okay, so more ideas using regular matter instead of that exotic negative energy stuff. What about that general warp drive model you mentioned earlier?
Right, the Bobrick-Martyr model.
Yeah.
That's a broader framework that tries to include all existing warp drive ideas and create new ones that don't have the same negative energy problems as the Alcubierre drive.
Sounds promising. What kind of warp drives does it allow for?
Well, it allows for slower-than-light warp drives that use positive energy, which is great, but it also allows for faster-than-light versions that meet certain quantum limitations, which are less strict than those classical energy conditions we talked about.
So bending the rules a bit, but not breaking them completely.
Exactly. And this model also emphasizes that any warp drive, if it's going to be real, will have to be some kind of moving shell of material. You'll need something to actually push it.
Makes sense. We can't escape the need for some kind of propulsion.
Right. And on top of all that, researchers are also working on optimizing the shape of the Alcubierre warp bubble using advanced math techniques. They're trying to reduce how much negative energy it would need, even if it still needs some.
So refining the design to make it more efficient. And what about Eric Lentz's work? Any updates on that?
Lentz has been focusing on using specific shifting vector fields, which are basically mathematical tools that change the coordinate system of the spaceship. He believes that the right fields could create enough positive energy density to avoid the need for negative energy altogether.
So finding a mathematical loophole that lets us use regular energy.
Kind of, yeah. He's been experimenting with different coordinate systems and shift vector fields to see what kind of energy densities they produce. He found that Alcubierre's original metric always needs negative energy, even with these coordinate shifts. But when he tried using specific polynomial and Gaussian shapes for the shift vector field, he found that, under certain conditions, they could create positive energy density.
So the shape of the field matters. That's pretty wild.
It is. He even proposed this crazy idea of a double-sided spaceship, with each side having its own coordinate system. He thinks this might make the spaceship invisible to outside observers under certain conditions, but it's super theoretical.
Invisible spaceships. Okay, that's definitely a topic for another deep dive. Well, we've covered a lot today. From the mysteries of subspace communication to the potential of the Higgs field, the weirdness of quantum tunneling, and the challenges of warp drives. It's been a wild ride through some truly mind-boggling concepts.
It really shows how much effort is going into understanding these seemingly impossible challenges. It's amazing to see scientists tackling these questions, pushing the limits of what we know.
And speaking of pushing limits, for our listeners out there, we have a question for you. Given everything we've discussed today, all the theoretical progress and the unknowns that remain, what do you think would be the key breakthrough to achieving interstellar travel or instant communication? What would unlock these seemingly impossible dreams?
It's a question worth pondering.
It really is. Thank you for joining us on this incredible deep dive into the cutting edge of science and technology.
We hope you enjoyed it.
This has been Teolumen Insights. If you enjoyed our exploration, please like and subscribe for more deep dives into the ever-changing world of science and tech. This is Teolumen Insights, signing off.